Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Introduction. The year 1905 marks a pivotal juncture in the annals of physics, a year that witnessed the genesis of several groundbreaking works by Albert Einstein, fundamentally altering humanity's comprehension of space, time, and matter. Among these seminal contributions, the paper, Does the Inertia of a Body Depend Upon Its Energy Content, published in Annal and Air Physic, stands as a monument to intellectual audacity, and its potential. It proposed a connection between mass and energy of unprecedented gravity. This essay endeavours to conduct a section-by-section critical evaluation of Einstein's work, illuminating its core claims, scrutinising its arguments, and assessing its implications. The aim is to move beyond a summary or a broad survey of the paper. It goes directly into a dissection of its internal logic, its methodology, and its conceptual originality, while also considering its reception by the scientific community and its influence on subsequent developments within physics. The ultimate goal is to provide a detailed, insightful analysis of why Einstein's paper continues to hold relevance over a century after its publication. Section 1: Introduction and the Principle of Relativity. Einstein opens his paper by framing the question of inertia, the resistance a body offers to changes in its state of motion, and its relationship to a body's energy content. A central assumption underlying the paper is the principle of relativity, which states that the laws of physics are identical for all observers in uniform motion. This principle, formulated in the context of the burgeoning theory of special relativity, sets the stage for his investigation. Einstein relies on concepts from his previous, groundbreaking work on the electrodynamics of moving bodies, published earlier in 1905, and presents the question to be investigated by considering the consequences of energy exchange. He lays out the groundwork for the core principle that any alteration in a body's energy content by some energy flow causes a proportional change in its inertia. It is from this foundation that Einstein builds. This careful construction of the problem within the framework of the principle of relativity provides the initial justification for the paper's subsequent arguments. The paper makes the assumption that the principle of relativity, which was already established as being successful in explaining a number of physical phenomena, would be valid here as Section 2: Energy Emission and the Loss of Inertia. Einstein moves through the paper's argument by first examining the energy content and inertia of a body when it emits energy in the form of light. Consider a body at rest, which, from our understanding, has some energy and some mass, and thus some inertia. Einstein then proposes it emit two pulses of light, each of equal energy, that travel in opposite directions. Consider further that this emission, as described by the principle of relativity, occurs in a second frame of reference, within which the body is moving. Einstein then explains that if this body, after the light emission, experiences a reduction in its inertia, then the emission of energy needs to be accompanied by a loss of inertia. Einstein then performs mathematical calculations, in which he uses L, describing the energy emitted in the form of light, and C describing the speed of light, being a constant, to relate them to the change in mass, m. He then shows that, in an inertial frame of reference, a body which has an energy loss of L emits energy in the form of light, and thus loses an amount of mass equal to L divided by c squared. He arrives at his famous equation, E equals m times c squared, although it is stated in the text as m equals L divided by c squared, representing that the change in mass is proportional to the energy loss and the speed of light squared. This section presents the central argument that the emission of energy, particularly in the form of light, leads to a corresponding reduction in a body's inertia, and consequently, a reduction in its mass. This conclusion, supported by the principle of relativity, forms the foundation of the paper's primary claim A critical evaluation of this section indicates that reliance on the principle of relativity and energy conservation is a necessary premise, that Einstein's mathematics is meticulously constructed. Section 3. Generalization and implications. Having established the relationship between energy loss and inertia in the specific case of light emission, Einstein undertakes a generalization. He broadens the scope of his conclusion to apply to any change in a body's energy content by considering that energy emission, although specifically examined in Section 2, is just one type of energy transfer. He posits that any change in the energy content of a body, regardless of the form of energy involved, will equally be reflected by a change in its inertia. This implies that the connection between inertia and energy content is a general principle, extending further than just the emission of light. One consequence, therefore, is the potential for matter to be transformed into energy, and vice versa. He suggests that if a body gains energy, its inertia will also increase, indicating that energy and mass are interchangeable. His work in this area suggested that many of the existing ideas about mass and energy conservation might be somewhat inaccurate in the most general sense. He points out that the energy content of an object, especially atomic nuclei, may be significant for an object's inertia. This observation anticipates the possibility that extremely small amounts of mass are able to be converted to large amounts of energy. The generalization of this idea, coupled with the principle of relativity, suggests the equivalence of mass and energy. Section 4. The equation E equals mc squared and its significance. Einstein then presents the equation m equals L divided by c squared again, but this time he frames it in a manner more consistent with modern notation. This is where Einstein states the equivalence between energy and mass. Any increase in a body's energy is an increase in its mass, and in an inert frame of reference, a change in energy is a change in inertia. As the speed of light is a very large number, c squared is an enormous number. This means that small changes in mass correspond to very large amounts of energy, and the converse. This relationship between mass and energy, as expressed in the now ubiquitous equation E equals m times c squared, is the central claim of the paper. The equation constitutes a radical departure from the classical notions of physics. It brings forward an entirely new way of understanding the universe and the interchangeability between mass and energy. Einstein also underscores the implications of this result and clarifies that the equation represents a very important fact concerning a body's inertia. This relationship offered the prospect that immense quantities of energy could be derived from a relatively small amount of mass. One of the most profound consequences of this equation is that it opened the door to understanding nuclear reactions, and as a result, the potential for both destructive and constructive uses. The very structure of the atom, with its immense store of energy in the nucleus, was now within reach of scientific comprehension. Section 5. The role of energy in mass. Einstein discusses the nature of mass as being comprised not just of the material content of an object, but also the energy within it. Classical physics views mass as a fundamental, immutable property. It is an inherent property of a body and it remains constant. A body's mass is its measure of its resistance to acceleration. Energy, on the other hand, is something that can vary. A body's energy can change. Einstein suggests a shift in our understanding energy might be an essential ingredient of mass itself. He then concludes that if an object emits energy equal to some quantity, L, the inertia will be reduced by L divided by c squared. This signifies the relationship between a body's mass and the energy content of that body. He then considers the implications of heat, which is a measure of internal energy. Einstein therefore implies that the inertia of a body will change if energy enters or leaves it. This leads to an argument suggesting that a body's inertia is connected to its energy, which he shows as equivalent to a body's content of energy. This discussion is important as it establishes the very close relationship between mass and energy, which Einstein would further clarify later with his famous equation. A crucial assessment of these ideas leads to the conclusion that the mass of a body will increase if it absorbs energy. Section 6. the impact of the work and its relationship to previous ideas. In examining the impact of does the inertia of a body depend upon its energy content, one is compelled to discuss its relationship to the intellectual landscape of theoretical physics in the early 20th century. Einstein's work did not arise in a vacuum. He was actively engaging with and synthesizing the ideas of his predecessors, while simultaneously forging an entirely new path. The principles of conservation of energy and conservation of mass, two bedrock principles of classical physics, were now shown to be two facets of a single more general principle involving the conservation of massology. The paper provided an explanation for the puzzling observation of radioactive decay, where some mass apparently disappeared. Einstein's contemporaries had not yet developed the theoretical or experimental tools to fully grasp the implications of his work. It was also realized that mass and energy were indeed linked. This paper, however, provided a conceptual groundwork for the evolution of quantum mechanics and a more complete understanding of the atom. Section 7: Methodological Nuances and Considerations. Einstein's approach to this subject emphasizes his theoretical brilliance. His strategy is built upon what is called a thought experiment, also known as a Jedidian experiment, which is a tool used by many great physicists and mathematicians. He considered the emission of light from a moving body, and he reasoned that the energy released by the body would be associated with loss of inertia. His method is firmly rooted in the principle of relativity and the laws of conservation of energy and momentum. The meticulous construction of the arguments, the clear mathematical derivations, and the insightful discussion of the implications stand as testament to the paper's strength. Through this logic, he arrives at his famous equation. Einstein's method also shows the power of theoretical reasoning in developing new insights into the physical world in the early 20th century. The key strength of the paper lies in its innovative utilization of theoretical reasoning and its capacity to build on established physical principles while simultaneously extending them. Section 8 critiques, reception, and subsequent revisions. This paper, initially published in German, did not receive immediate widespread attention. Yet, as the implications of special relativity became apparent and as experimental evidence supporting the equivalence of mass and energy emerged, the paper's significance gradually increased in the minds of scientists. Despite the foundational importance of the paper, Einstein undertook some revisions and refinements. The language was altered to more precisely reflect the relationship between energy and mass. Even though the idea had enormous consequences, early applications of this work to the field were difficult. The initial paper also gave rise to some debate about the precise nature of the energy-mass equivalence. Einstein's later work on general relativity would provide a more coherent framework for understanding the relationship between mass, energy, and gravity. The paper, although brief, quickly became a foundation of modern physics. It established a new paradigm regarding mass and energy. Section 9: The enduring significance of the work. The profound legacy of Einstein's "Does the inertia of a body depend upon its energy content?" lies in its transformation of our understanding of the physical universe. The paper not only established the equivalence of mass and energy, but provided the crucial underpinning for nuclear physics and the possibility of atomic energy. His insight was revolutionary. It not only provided a correct interpretation of prior observations, but also made predictions about future observations. It is a concise, yet profound, piece of work that serves as a testament to the power of theoretical physics in revolutionizing scientific thought. The relevance of this paper is seen today in everything from nuclear power plants to medical technology, demonstrating the impact that the fundamental scientific discoveries of this era have had on our world. His approach, his reasoning, and the enduring implications of his equation have made it a staple of modern physics, shaping not just science, but the conclusion. In conclusion, Albert Einstein's 1905 paper, "Does the inertia of a body depend upon its energy content?" constitutes an indispensable contribution to the development of modern physics. Through a meticulous section-by-section analysis, this essay has illuminated the paper's core claims, its method of reasoning, and its lasting significance. It has shown that Einstein's arguments are based on the principle of relativity and the law of conservation of energy, and that his conclusions have served as a cornerstone for nearly every major breakthrough in the physics field over the last century. The paper's enduring impact lies in its revelation of the profound interconnectedness of mass and energy, as represented by the equation E=m times c², and its far-reaching implications for our comprehension of nature. The paper has also been a source of considerable scientific and technological progress. The enduring relevance of Einstein's paper resides in its capacity to inspire generations of scientists and thinkers. It serves as a constant reminder of the intellectual power that results from delving into the fundamental questions of existence. This is a paper that not only changed the landscape of physics, but also transformed our understanding of the universe and our place within it.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.